Okay, bingo. Hey, this is the last talk, I believe, of the day. Yeah. Mr. Katz has a tremendous security background to him. And, well, I'll let you talk about yourself there. And I want to know what you got going on with JavaScript Obfuscation.
Sure thing. Thank you very much. Hi, everybody. So I'm very excited being here today. It's been over 2 years since I last was doing in-person presentation. And the last one that I was doing was BSides San Francisco 2020. So it's closing a circle in that sense. And I'm here today to talk to you about JavaScript Obfuscation. It's all about the packers, right? And I wrote packers with dashes, and we will go into that later, but remember that. So let's start at the beginning. We'll do a short introduction for myself. Former OWASP Israel chapter lead, really enjoyed doing that. I'm a data-driven security researcher, which means I work with a lot of data, and data is something that I'm using on a daily basis to create a lot of my research. And we will see some examples for that here today. When I try to define my role, I'm saying that I'm trying to move security challenges into the science and solution space, and hopefully we'll see that here today as well. And I have a very boring social network persona, therefore I encourage you not to follow me in any given way in Twitter or in any other platform. Don't do that, right? Boring. Okay, let's continue. How did I end up here today? So over 18 months ago, I was doing some research about JavaScript Obfuscation. And in that research, I released 3 different blogs. The first one was, in the first one, I was trying to actually do a dictionary-based kind of techniques being used to do obfuscation. That was the first blog. The second blog took some of phishing data that I had, a really good one, that I was looking into that, and I had the ability to say in the context of trends, how many of those phishing websites are being, JavaScript Obfuscation is being used on those phishing websites. And the third one, I took one sample of JavaScript being obfuscated, a very, relatively small example because they could be huge. I needed to do some snapshot for that. And this is the snapshot of that given sample that I did reversing for that sample, going step by step, breaking up that to smaller pieces to try to better understand, better explain what happened when something is being obfuscated. And while I was doing that, I started to ask myself the question, well, that's a nice thing. It took me a couple of hours at the time, but I don't have the capacity to doing that. And the amount and volume of samples of JavaScript being obfuscated in the wild that I'm seeing is way too much for me to analyze. So I asked myself, maybe I can do some sort of a research project around that. And I had few objectives for that research project. The first objective was to try to figure out if I can find a technique that can enable me to detect JavaScript once being obfuscated. But more to that, it would be nice if I could say that the obfuscated JavaScript is actually malicious. So that's the first objective. The second objective was, well, I need to do that at scale. It's not a matter of 1 or 2 or 10 or 20. I need to do 100 or even 1,000 in a given time frame. The third objective, which is actually related to the second one, is me saying, okay, so I want to analyze those files, but I have some limitation, right? When it comes to JavaScript, you can take the file, the JavaScript itself, you can render it and see what's actually being executed. But that's something that I didn't want to do. From my point of view, I need to look into a file as the file being transferred from the server to the client being executed there, look at the file before being executed and make a decision based on that. And that's actually a statistical analysis kind of approach, which has better performance when it comes to analyzing those files, because obviously when you need to render a page and look on the execution of the page, that obviously had performance impact, and that could take some time. Now, the first objective that I have is assuming the Pareto principle, which says the following thing. Well, if I will take 20 of the most used JavaScript packer is actually software that's doing obfuscation of a given JavaScript file, and I will look into them, I will be able to see that 80% of the samples out there are being used by those 20%. So in other words, I'm not trying to solve the entire spectrum of problem of JavaScript obfuscation. I'm trying to do a minimal effort and solve as much as possible in the space of the problem that I'm trying to solve. So, and here are some of the links of those blogs from over 18 months ago. And I started the project, and I started with a couple of questions that I had in mind. So the first question is why and how JavaScript is being obfuscated, and we'll go through that and we'll answer that question. The second question was, what are the numbers behind the usage of JavaScript obfuscation in the wild? And that's an interesting one. Well, I didn't know what's this, the volume or the scale of that problem, and I had to well, as part of the research, wanted to know that answer and being able to report on that. The third question that I had in mind, well, will I be able to find a solution for the problem to be able to detect an obfuscated JavaScript, to find a technique to be able to do that? And the third question, well, and that's a question that I would give you the answer, but we'll get into detail later on. Does JavaScript obfuscation mean malicious? And the answer is no. We'll go into that in details, but obviously JavaScript obfuscation can use for malicious purposes, but it can also be used for benign purposes as well. So let's do touch base. Let's try to figure out what does it mean JavaScript obfuscation and what's the challenges of that. So here you can see 3-line code of JavaScript, hello world kind of example. And if you take those 3 lines of code and run it into an obfuscator, a packer, a software that knows to take a given JavaScript code and do obfuscation for that code, it will create, and you cannot see the example itself, but believe me, it's not readable. It's very hard to understand. It became much bigger in that sense. And if you take those 3 lines of code and do the same obfuscation with the same tool, 1 second after you did the first kind of obfuscation, you will get a different file. And when you compare those files, they are not the same. So when we talk about some of the problems that I experienced with in the context of JavaScript obfuscation, for example, the ability to take a file that was identified as malicious because it was obfuscated, and we know it's malicious, and try to create a signature for that file, meaning a text-based signature or a hash-based signature, and trying to detect that file will not work. Because if we will take the same file and do an obfuscation 1 second after we did the previous obfuscation, we'll get different file, different signature, and that's a problem, right? That's part of the problem I want to address. So that's a bit introduction. How JavaScript is being obfuscated, and here are the most, well, the common, the most used techniques being used out there for obfuscation. Using repetitive or meaningless, whether those are function name or variable name, making that a bit unreadable in that sense, the file itself. Using anti-debugging code, meaning putting into the code some code that will make the debugging much harder. It's not impossible, but it makes it much harder. And third element here is will consume computing resources and time. And in other words, if you put into the code dead code, meaning code that be executed but doesn't do anything, or you put timers in that sense, you make a given code being very slowly, and in the context, again, in the context of resources, that takes a lot of time, and we don't always have those resources. So we talked about the how, let's talk about the why. Why JavaScript is being obfuscated? So the trivial thing is that JavaScript is a client-side code. It's run on our browser in most cases. And as such, it's a code that is exposed to us, meaning we can see the code. We can see it on our browser. And that's versus a server-side code that once being executed, we don't really see the code and we don't know really what's the functionality being executed. JavaScript, we have the code, we can analyze that code. And that's a challenge, right? It's a challenge from a offensive or defensive point of view, depends on how you look into that, is if you want to make sure that that code is unreadable or it's very hard to understand that code, well, in the context of security by obscurity, making the code harder to read or harder to debug makes sense, right? It's not, again, impossible to understand the code and what does it execute, but creating obfuscation makes it much harder. And the second reason, as I mentioned before, if you do an obfuscation, you create much more challenges from a defensive point of view, because if you had some sort of a signature, whether that's text-based or hash-based, on that code, it will not be successful. Now, I have my own interpretation of the reason why JavaScript is being used in the wild from a malicious point of view, right? And that's my perspective, and hopefully you will agree with me, is that from my point of view, it's all about some sort of an equation that says when you have more resources and more time, from a defensive point of view, that will result in lower detection rate. Meaning if me being attacked by someone that create an overwhelming amount of work for me. And that work creates the need for more resources, whether those are human resources or whether they're computational resources. It will take more time, and as a result of that, detection rate will be lower. It will not evade detection, but it will be lower. And in that sense, from an adversary point of view, they will have a higher success rate. And that equation is what drives the usage of JavaScript and obfuscation of JavaScript in the wild. Now, so at that point of time, I had some question, I had some assumption. I started to look into a lot of JavaScript samples. And when I look into those samples, 4 different samples crossed my attention in that sense. And I took a snapshot of 4 different samples. And a snapshot of 4 different samples. And when I look first on those 4 different snapshots, I told myself, well, they're not the same, right? If you look into them, if you go, letter by letter or character by character, they are not the same, but they look very similar, but they are not the same. And why they are not the same? Because they represent different threats. The 2 upper ones represent phishing pages. One is financial services. The other one is storage services. The 2 lower one, the right one is a dropper, malware dropper, and the left one is Magecart, JavaScript trying to steal some credential or, sorry, some credit card information, stuff like that. So they are definitely not the same. These are not the same file. It's not the same threat, but they are very, very similar. And the similarity is when you do some sort of a zoom out to them, you can start to see that there is some sort of a pattern here being executed. You can see an anonymous function with 2 variables, and in that function, you can see a variable that contains a function that has a while with a decreasing kind of element into that, and there's some pushing and shifting, which is doing some sort of a rotation on a given payload, on a given array that is being given to that function, and that's a structure, and that structure repeats itself. The values of parameters of functions and a bit, let's say, some code can be added to that given function, but the structure is the same. So I asked myself, maybe I can work with that structure. Maybe that structure can help me do some sort of a detection. So I was saying, hey, how can I do that? Let's take a given JavaScript file, do some sort of a representation of that file in an AST format, which is an abstract syntax tree. An abstract syntax tree, take a given code and do some sort of a JSON kind of representation for that. So now I have a JSON which has some sort of a structure, and I can go over that JSON file and make a decision or try to look for the given pattern that I was looking at the beginning. So in our case, the functionality that you see, if we will take this structure and look only for a given specific, specific part of that structure, enable me to detect a structure of the code or some sort of a pattern of the code that is not dependent on the values or some of the parameters of functioning being used in that code. So I created a proof of concept for that. And before creating proof of concept for that, I used 5 different packers, and I look into those packers, as I said before, the most used packer that I was able to see. And I created signature for each one of those. So we will go through that really, really quickly, but you can see these are some of the examples of those packers. Very straightforward one, basically doing, in most cases, some sort of a manipulation of payload. Payload that was, we had an original kind of JavaScript code. That code was obfuscated and created much larger with a payload kind of outcome for that, and that payload, once going to this code, is being reversed in that sense, in being decrypted, and in order to get to the original code that was obfuscated at the beginning. So we have 3 of those, and we have these 2 that are more common one. You can see that example number 4 contains I named it packer with dashes, and the reason for that, you can see that the name of the function get 6 parameters, and those parameters values are P-A-C-K-E-R, and that's the reason why I called it that, and we'll address that later on. So we now know that we have a proof of concept. We know that we have 5 different JavaScript packers that I created signature, a structure-based signature for them. Now the question is, what are the results? What we are seeing out there when I'm using that proof of concept that I just created in order to see if I have detection, what is the amount of, well, numbers that I see behind that detection. So here we go. The first data set that I was using was a phishing data set with over 100,000 different phishing pages. Now, I want to say that given data set was not as clear as I wanted that to be. It wasn't clean, sorry, not clear. It has a bit disruption in that fact. Some of those phishing websites were not phishing website or used to be phishing website, and now they were mitigated. So it was not clean data set, but still I was able to see that I have 2.1 detection rate on that data set, which means, in other words, that the concept that I had, meaning I have some sort of a proof of concept to try to detect a structure of JavaScript, is working. I am seeing detection. And more to that, I validated those detections, and those were actually the detection that I was expecting to see. It wasn't some fault in that sense. The second data set that I was using was a much more both malware and crypto miners and Magecart and some phishing website, but it was very, very quality in that sense. And on that given data set, I was able to see that 26% of the JavaScript pages that were examined were actually obfuscated. And that's a really big message. And the message is that we are seeing some sort of a shift in that sense on threat landscape, where threat actors understand that they can challenge us from a defensive point of view, and they need to do that by doing obfuscation. And obfuscation makes their attacks much more successful, again, as we mentioned before. And important to say in that context that this number, the 26%, is very, how should I say it? It's a very realistic number. It's not an exaggeration. It's not a over-optimistic number. It's really realistic, meaning the numbers I would expect are much higher. Now, we did testing for data that was classified as malicious. Now comes the question, what about data that is not malicious? Would we be able to see some detection? And the answer for that is yes, we were able to see detection. We took the 18,000 most popular website on Alexa, and we checked them out. And we were able to see that 0.5 of those pages were actually also using JavaScript obfuscation. More to that, we took a random kind of set of URLs and we checked them as well. And the numbers were very similar to that. And the meaning for that is that we are now understanding that in some cases, JavaScript obfuscation is being used also for benign purposes. And why we know that? Because I was going over some of those samples, and I wanted to make sure that those are actually true detections. It's not false positive in any way. Now, I would assume you have some questions on, so why they are being obfuscated. So why does a benign website doing obfuscation? That's a really great question. We'll address that in a few seconds. So summary of what we have seen so far. So we are seeing that JavaScript obfuscation detection is accurate, right? So I created a technique and it works and I have really good results, which is a good start. We were able to see that using that technique, I'm actually having over 4K new detection of malware and phishing pages. And again, as a result of my objectives that were to increase detection in that sense, to be able to detect all kind of obfuscated attacks that in most cases will evade traditional kind of detection mechanism, I have a nice outcome. We were able to see that some of those packers are mostly associated with malicious activity. For example, the AES CTR decrypt packer that in most cases is being used for phishing website, and we didn't saw any true detection of that given packer being used on benign website, and therefore that can lead us to a decision-making kind of approach. Meaning if we can see some pages being obfuscated with that given packer, most likely that given pages are malicious. And finally, we were able to see that obfuscation is not equal to malicious, right? And that's a problem. And that problem, well, resolved with two questions. The first one is the one that I just asked. So what's the reason for that? What we are seeing out there and why benign websites are being obfuscated, or benign JavaScript file being obfuscated. And the second question is, okay, so now we have a problem. We know that some are malicious and some are not. Can we introduce an approach that will solve that problem, that will enable us to do better detection? And we'll try to address those two questions. So the first one, so why benign websites are being obfuscated? Here are a few of the answers for that. According to the files that I was able to see, I would assume that there are other better reasons as well. But for example, email address masking. For some reason, websites, some websites, in order to make, want to include email address in the website, but doesn't want to make that email address available to any kind of scanner or search engines that look into their website, and therefore they are doing obfuscation for that. Cookie client side functionality, don't try to ask me the reason for that. It's not good practice, but yet we were able to see some of those examples. A lot of examples for third-party scripts, such as advertisements and translation services, that using obfuscation. And what's the reason for that? So try to imagine that you have a website, and that website consumes a third-party script that do some sort of a translation service kind of functionality on your website. That third-party vendor is doing obfuscation of that code and push that code to your website, and that's the way it's being used. Again, they have their own reasons. I would assume that security by obscurity, that's the reason why they are doing that. And the last example that I will try to avoid addressing is that a lot of adult content are also doing obfuscation, and I will avoid addressing that issue. So we try to answer the first question, right? And the second question is, so can we build a mechanism that will enable us to, after we detected that a given file was obfuscated, can we take it to the next level and try to differentiate between malicious and non-malicious obfuscated file? In order to do that, I use two kind of approaches that are complementary in a sense, right? The first approach is a false positive kind of approach to try to say, hey, let's try to take those benign websites that are in most cases highly popular, because that's the problem that we're trying to address. And let's try to figure out if we can find techniques that will enable us to say that at least few of them are obfuscated, but we know how to say that they are benign and not malicious. So that's the first approach. And the second approach is a true positive kind of approach. And in that approach, I'm trying to show, and again, in a high-level kind of sense, machine learning approach for classifying malicious files, and we'll go through that. And again, it's a high-level and example, and hopefully it will make sense. So the first approach, false positive, right? So we have a highly popular website. That's the gray circles, the Alexa and the random data set that we have. And for each one of those files on those domains that are under those kind of data sets, we have files, we have, JavaScript code that we hash that JavaScript code. And we associated the hashed JavaScript code to the actual domain names, which are the blue circle. So orange means the hash value of a JavaScript code, blue means domain names, and the gray one is the big circles of Alexa and random data sets. And what we were able to see is that actually, in a lot of cases, we can see that the same files are being obfuscated, but the hash value is the same. And that can be addressed by the example that we saw before on the translation services, because they are taking a given code, doing obfuscation of that, and push that code to many different websites. And therefore, you can see the same hash value for that code. So in other words, the false positive and a whitelist kind of approach would say, hey, let's take those files that are being pushed to a lot of, to many different highly popular websites and do a whitelist approach for that. Let's make sure that if we see a file with a hash value of that given, the value that we see here, we can classify that as non-malicious, and by that reduce the problem that we are facing. And again, in my case, which was a very small set and a very limited kind of data set that I was using, I was able to reduce the problem by 20%. And obviously, if we will use a much larger data set of benign files, we will get to better numbers. So that was the first approach, right? The whitelist approach and positive security kind of approach. The second approach was true positive, right, and machine learning. So we saw at the beginning a file, a JavaScript file, right? And we saw how we break it into small pieces and try to de-obfuscate that. Now, you can look at that file from a machine learning approach, which is a set of features that can be extracted from that file. So for example, if you have an array in that file, which that array contains the actual payload that's being used or being de-obfuscated as part of that file, we can look at that array and say, hey, the amount of elements in that array could be considered as a feature that we can use later on. The length of the values of the elements of that array can be used. The entropy of the values can also be used. We were able to see that a lot of those obfuscated files contain a lot of parameters and function names. Now, counting those, and I'm calling them identifiers in that sense, counting them is also a feature that can be used in the context of doing some sort of a machine learning approach to try to identify or classify who's malicious and who's not. So here is an example. I took the data set of those samples that match on the push shift packer. That's one of the 5 signatures that I had, the structure-based signature. So I took one of those, and I put them on this graph in the context of using 2 different features here. The first feature on the left is the number of unique identifiers, which means the number of parameter values and function names. On the bottom side, you can see a different feature, which means the number of elements that we can see in a given array in that file. And only by using those 2 features, right, a very naive approach, we start to see that there are different classifications, right? We have green, red, and blue. Green mean malware, blue mean Alexa, and blue mean random, and red mean Alexa. So in that sense, we started to divide the space to 2 different groups on the right side and on the upper left side, and those groups by themselves represent malware with the features that we chose, only those 2 different features that we chose here. And that gives us the ability to make decisions. We'll see those decisions in the following slide. But wait, we have at the center of this graph a mixture of colors, right? So we can also do some sort of focus on that group as well. And when we will do that, we can see that even in that group, we have an even smaller set of features being classified, and we can also use and apply a machine learning approach to also make decisions based on that. So how does it look like in the context of machine learning? So I took I took 3 different features, the 2 ones that I just mentioned, and a third feature that I will name in a minute, and I created a decision tree, a malware decision tree kind of module that enabled me to make decision. And again, it's a very high level, and I didn't spend a lot of time of tuning that. It's more about proof of concept and showing that it can be done. So when we take only the most right side of that tree, meaning we are using 3 features. The first one on the top is number of identifier, which are function name and variables name that start with _0x. That's a feature. The second feature that we use is the number of values in a given array, the elements, the number of elements. And the third feature was the number of unique identifiers, which, again, identifiers are parameter names and function names. Only taking those 3 features with the following values, meaning if you can see number of identifiers starting with _0x above 20, and we can see number of elements in array that is about 17, and we can see that the unique identifier is greater than 92, only those 3 features and those values will eliminate 50% of the problem, meaning 757 of this, out of the 1,541 samples that we checked. So that's, again, an example how we take a file, create the right feature out of that file, create a decision tree based on that, doing some fine-tuning for those different features, making the right decision. And by that, we can classify a given file that we know it's been obfuscated, but we don't know if it's malicious or not, to being malicious or being benign, right? That's the approach that I'm suggesting here. Now, we had 4 questions at the beginning, right? why and how JavaScript is being obfuscated, and I think we addressed that. We had what are the numbers behind the use of JavaScript being obfuscated in the wild, and we were able to see that, for example, 26% of the malware data set were classified as files that are being obfuscated. We addressed the question that obfuscation doesn't equal to malicious, right? And more to that, we addressed the question on technique that enable us to differentiate between something that is malicious versus something that is benign. So that part of the research was done. There is some step in the research that I would like to do in the coming month. And here are some of the things that are on my to-do list. I want to release that code, right? I need some work doing that. I need to allocate some of my time to do the work doing that. I want to add additional signature for additional packers. I want to refine some of the data sets that I was using, trying to use better data set, as a result, have better result and better functionality being done. And I want to use maybe more features in the module of the machine learning module to make better decision, being able to classify things much better. And explore the ability to do some sort of an algorithmic extraction for patterns in signatures. So I named the presentation, it's all about the package, right, with the dashes. And I told you, hey, what about those dashes? And I also showed you that's the reason for that, right? I'm not sure that you can see that. You can see that. So the name of the variables in that function are P-A-C-K-E-R, right? And part of the approach that I was using was saying, hey, the name of the variables are not interesting for me because they can easily be changed. And I was doing the right decision because after a while, I was able to see a different example using packed instead of packers, which was a good decision at the time. But as I continued to look into more examples and more sample, I suddenly saw the following example, which is, again, the same structure, but this time you can see the name of the variable are underscore 0x176 and so forth, right? Making it very readable. And therefore, I was saying to myself, maybe I should change the name of the presentation to it's all about the underscore 0x. I don't know. We will consider that. We'll see. So I think that was me for today, guys. I hope that you enjoyed the presentation. And if you have any questions, feel free. Here we go. I think he wants you to speak to the mic.
Very good. Well, I have lots of questions, but I'll start with one.
Okay. I will do them.
So you detect 26% of the malicious of obfuscated samples with your 5 packers.
All right.
How many obfuscated samples were not detected because you didn't have code to recognize the obfuscation in that data set?
Mm-hmm. So that's a great question. I don't have a clear answer for that. I have my intuition. Because again, if I knew what I'm missing, I would easily add a signature or a structure-based signature for that. So I know the numbers are much higher, toward the 50%, but it's becoming more of a niche or more small kind of packers being used, and I didn't have the resources and time to take each one of those packer and figure out what's the structural data signature that I want to pull out of them. So numbers are high, but I don't have a realistic number to share with that.
But in the machine learning model, the arbitrary features that you recognize would probably apply to the rest of the packers as well. Would they not?
It's correct and not 100% correct, because the machine learning approach was to take a data set that was already classified as being obfuscated by one of the packers that we have and make decision based on that, whether that's benign or malicious. So in that, it will to create some sort of a machine learning approach that generically can detect an obfuscated code is a bit too overfitting in that sense, right? Okay. Because the feature might be different to different packers, right? Yeah.
And where did your data come from?
That's a good one. A lot of the data that, like, part of data that we have in my work environment.
Oh, I see. It was Akamai data rather than APWG yes. Or...
Yes.
Okay,
yes.
Thank you.
Thank you. I really enjoyed the talk. Thank you for that.
Thank you.
You showed us a few packers, but you identified them via their signatures, via the patterns in the code. But clearly everyone is using similar things. Do you happen to know what vendors or I don't know if there's free software out there that everyone is using for this.
So it's a great question. First of all, I didn't go into the vendor space of obfuscation. That's a different, as I mentioned at the beginning, the Pareto principle, 80-20. I'm not into looking into those that are creating APT kind of, specially crafted obfuscation or someone that is using a vendor-wise kind of obfuscation. It was more of the open source or online kind of packers that I was able to track, and those were the ones that were massively used in that sense, in the context of numbers. So I was more focused on those. Did I address the question?
Yeah, thank you. I was just mostly curious if there are, I don't know, popular projects that represent what these packers generate.
Different use cases, different,
Sure, thank you.
Most of them online. It's like, I would assume that you will do a Google search for doing an online obfuscation, and you will get into some of them really easily.
One other question that I had, if that's okay, is you mentioned at the beginning of the talk about taking these this obfuscated code that was packed and it has a similar structure but dissimilar identifiers, and turning those into an AST to look for the patterns that way. And then I didn't understand if you did go with that approach or if you used a machine learning model that was something different, and why didn't you go with that?
I did that approach. That was the first phase of creating a proof of concept tool that for each packer I created a structure-based signature, right, using the concept of AST and looking into the patterns that are really relevant and repetitive in the context of a structure. I was taking that given proof of concept tool that I wrote, run it on a lot of data sets, and that's the result that I was showing. And on those results, we were able to see that some of my detection shows that obfuscation doesn't mean malicious, and that led me to move into the machine learning approach to try to differentiate between malicious versus benign.
I see. Thanks very much.
Sure.
Okay.
Hi. You mentioned some of the false positives that you saw. By any chance, did you see anybody actually using it not for malicious that would show up in the false positives, actually for more, well, security reasons?
So false positive is a I need to frame the concept of false positive on this research. Because in the context of me creating proof of concept tool that know how to detect those packers, I didn't have any false positive, meaning I didn't detect structures that were the same structure that being used for obfuscation, but actually are not being, it's not obfuscation, it's something entirely different. I didn't have that kind of false positive. I think what created the sense of false positive is that we were able to see that some of the packers being used in a context of malicious intent, and some of those packers are being used in the context of benign, and that created some sort of a sense of false positive, but I didn't have any false positive in that sense.
Oh, gotcha. So no, I totally get that. I was just curious if you saw other use cases around the benign for obfuscation.
The examples that I gave in an email and the cookies, those were the most used one. But again, it's very these are open source kind of services. You can go into that, take your code, obfuscate it, and put it in whatever you want to do with that. And in that sense, the scars are the limit.
So I question your belief that it's expensive to expand these to the point of the eval and actually look at the content and decide if it's malicious or not. Although it's great that you tried to recognize obfuscation, I think you actually have to take it to the point where you look at the content to figure out if it's malicious or not. So, but in theory, one other point, the ML proponents would say ML is adaptive when the adversary changes their pattern. So I think it's great that you went from the AST model into something with ML, because that might scale much better with adaptation of the packers. Anyway,
yeah,
this is also my area of research.
So
I'd love
I
to talk to
totally
you more.
agree in that sense. And obviously, when I was trying to do things that are more generic in the context of machine learning, I started to see results that are not really make sense. But when I focus my machine learning per packer and the result, that put more of the feature are more associated with the packer and the action that packer makes. And that makes more sense to make a decision based on that. And obviously, these are statistical decisions, right? It's machine learning. It's a matter of statistics. So statistically, I had good result. That doesn't mean that you can also make mistakes, right? Depends on how the model works.
Thank you for the talk. I have three quick questions. So you kind of answered the first question. You want to extend the experimental part of your approach. I was curious to have more details about the data set, so I'm going to skip this. And the relationship you showed between different hashes, where did you get those relationships from?
So think about it like that. So we know we have benign data set that we know that there are matches of JavaScript being obfuscated on those files that are benign. And on each of those files, I took the JavaScript component out of those files, the section of JavaScript components on those files, and created hashes for those JavaScript parts of that files on those pages, and create hash values for them, and just save that. And then I was just doing some sort of a plotting of that and showing the relationship between them, and that showed me the fact that, well, I can see two different websites that both of them are highly popular, right, according to Alexa. They have, well, I'm working in Akamai, so we have a lot of data to back that up and try to figure out what does it mean, a popular website, and they were all in that sense. And I was able to see it's actually the same kind of code being hashed. So it's a different use case from the scenario of adversary kind of point of view of taking file and doing each time obfuscation, creating a version of that file and deploying that in different contexts. It was a use case of someone creating security by obscurity, taking the same code, doing the same one-time obfuscation, and push that to different websites, and that created the relationship that I was seeing there.
Thank you. And the last question is, you said some packers are more associated with malicious activities. Mm-hmm. Why do you think is that way?
That's a good question. I didn't thought about it, but I can try to think of the fact that maybe they were created by adversaries, therefore they're being used by them. Some of them probably being introduced in the context of, for example, phishing kits that are including those kind of packers as part of the phishing kit and being used in that context, and are not as other packers that are actually online websites that really good and very nice website that you can create different configuration of the obfuscation that you want to do, and everybody are using that, and that's a service, right? So maybe that was the reason why we were seeing different results.
So I have a question. It's
Of course.
when you say the malicious JavaScript, as you were saying, pointing out like maybe phishing campaigns or something, are you also like maybe looking at use after free attacks on JavaScript engines within browsers? Is that?
That's an issue that I didn't go to that direction, and my assumption was that I'm focused on JavaScript file being obfuscated, and how can I detect them while they're in transit? That was my approach.
Okay.
In that sense.
Other questions? Great.
Yeah, so I arrived towards the end of the talk, so you may have covered this towards the beginning, but so from what I understand, it seems like most of the analysis that you did was static, right?
Yes. So at the beginning of the presentation, I used 4 different objectives that I had at the beginning of the project, and one of those objectives was that in the context of my research, which is related to my work and some of the things that I was doing, I was looking for a solution that can do static code analysis, meaning I don't have the privilege to do rendering of the page and looking into JavaScript once it's being rendered. Mm. It needs to be decision-making on the file as it's in transit.
Okay.
And therefore, I use the static code analysis approach, which is much more performance effective, because that's also one of the objectives that I had.
Okay, that makes sense.
Okay, other questions?
How do we get in touch with you if not through your social media?
That's a good one. LinkedIn, that would be a great approach. We will find a way to get in touch.
Okay, others? Any comments, questions, stimulating ideas?
It's the end of the day, you know, people are,
Yeah, hey, it's
and I'm on, I wake
time to
up
head out.
today early Massachusetts time, so I'm like on my last few drops of fuel.
well, thank you very much for coming.
Sure thing. It
I've
was my
learned
pleasure.
a lot here today, so that's for sure. And you've been a fantastic audience. I hope you enjoyed B-Sides. Lots of things here to do in San Francisco. Go to the hate.
Thank you for you know, working with us the entire day and doing all those presentations and all that great introduction. And
Oh, thank you. It's been fun. So come back next year.